Okay, Kepler really gave us 3 laws of planetary motion, and all those PhET activities last week really were Kepler's 3 laws of motion. And those 3 laws of motion deal with what?
Newton.
What force? What force are they dealing with? Gravity. And the gravitational pull or force between 2 objects depends upon what 2 factors? We discussed this earlier. What 2 factors? Gravitational force is dependent upon what 2 factors? Nope. Distance between the objects. As we know, as you increase the distance, gravitational force goes down. What else? Mass of the objects. The greater the mass of the objects, the greater that gravitational force. So it really depends upon those 2 things. As you're going through the PhET activities, especially the 2 ones about the solar system, what did you notice about the speed of a planet in its orbit? Was it the fastest closest to the sun or the fastest the farthest away? Because gravity has a larger force there. All right. So things we've discussed some of these before. So we're going to put an ellipse up there, and this is already in your notes. I'm just reviewing what's in your notes. And what are the 2 points inside the ellipse called? The 2 points inside the ellipse. Yes. Not yet. And they're equidistant from either end of the ellipse. What are the 2, guys, you gotta listen. It's in your notes. We're not looking at our computers. We've got our notebooks open at Kepler's first and second laws of motion, notwithstanding Mr. Staublin dying by the hands of the great Obi-Wan Kenobi. What are the 2 points inside the ellipse called? It's in your notes. It's in your diagram. In fact, one of them's got even a special name. The what? Yep. And in an orbit, one of those is referred to as the sun, because we're doing orbits. Yeah, is it foci? I've heard it's foci, right? I think I've pronounced it foci. I think I've heard that one time or another too. So the foci. So those are on the ellipse, and they are inside. The line that goes through those points from end to end is referred to as that is the major axis. That is the length. If you want to think of it like that, that is the length of the ellipse. That's the length of the ellipse. The line that bisects, that is a semi-major axis. So when you talk about his first law, he's talking about the sun at one of those points, and then we have the orbit. He also mentioned the point closest to the sun is referred to as the what? Perihelion. Boy, somebody took some good notes. The point farthest away from the sun is referred to as what? Aphelion. The moon here, back when they had the super blood moon, it was the closest to the Earth that it's been in a while, and that is referred to as not perihelion, but perigee, when it's in reference to the Earth. Satellites have a perigee and they have an apogee. When it's in reference to the sun, it's aphelion and perihelion. So we have those 2 points going on. What else you want to add about Kepler's first law? Okay, eccentricity, the term eccentricity, very good. Come on, go. What's eccentricity really telling you? All right, how oval, how elliptical shape the planet's orbit is. If it is a circle, what is the eccentricity value? 0. So when you have an eccentricity value of 0, that means you have a circle. Eccentricity, and I'm just going to call it ECC, how do you find it? Divided by what? Come on, this isn't writing too well. The length of the major axis. And when you start talking the solar system, quite often, what units are you going to use?
Centimeters.
Well, probably in an experiment. But when you're talking solar system, what's kind of the basic unit in the solar system? We've already had this before, too. Not a light year. An AU, an astronomical unit. The distance between the Earth and the Sun. That value typically, is it going to be a whole number or is it going to be less than 1? It's going to be less than 1 most of the time. Because these 2 points, the foci, if you will, are what? Inside of the major axis. So this number on top in the numerator is going to be smaller than the number in the denominator. So you're going to have a number that is less than 1. Your notebook should be open. I think I've said it like 5 times already.
It's open.
No, it's not. When would it be 1? When would be the eccentricity be 1? Guys, just do the math. When's it going to be 1? When it's the number in the numerator is the same as the number in the denominator. In other words, when this distance equals that distance. The vast majority of times, though, it's going to be less than 1. So if you have an eccentricity of 1 means both the foci are what to each other? They're what? Yeah, really. These 2 are moving until really they're what? If there's no distance between them, they're right on what of each other? They're on top of each other. It's the same point. Hence, you have no distance between them. Anything to add to this one? All right, let's look at number 2. Yeah, just set it down. You're fine. I don't like that one. I want it. What's Kepler's second law state? Very good. In orbit, and again, we're speaking solar system here. will sweep out equal area in equal time. These two distances on the ellipse, if they are equal periods of time, 1 AU, 0.5 AU, whatever they happen to be. If these are equal time, the area is going to be, guys, you just told me it, equal. Which leads you right into the whole idea. We're not watching it, we're watching this. At what point in an orbit is the planet, the satellite, traveling the slowest? Yeah, really, when it's at aphelion. When's it traveling the fastest? Perihelion, okay. Let's say it's going counterclockwise. As it's moving from this point to aphelion, what's happened to the velocity or the speed? It's slowing. Yep. As it gets back into that whole gravitational field, it's getting closer, closer, closer. What's happened to the speed? It's getting faster. It's almost like you ever take some type of ball or anything, you throw it in the air, starts out fast and it's slow, 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 until it reaches the top, and then it starts to fall again. And then as it's falling, it's gaining what? Velocity. You guys writing this down, right? I know. So when you start looking at this, slow, slow, slow. Now it's starting to get pulled back in. And that is why when you start looking at an ellipse, it moves pretty slow here, but it moves faster as you approach the sun or that center of gravity. And again, gravitational pull is dependent upon distance and mass of the objects. Very good. Anything to add? All right, let's look at the third one. What's Kepler's third law? Orbital period is measured in what units? Period is measured in not light years, but years. And what's the standard year, the standard period for anything is compared to the orbital period for what planet? Earth. So if something is greater than 1, that object is farther away. Its orbit's outside the Earth. If the object has a period of less than 1, that object is closer to the Earth. Very good. A is really, they talk about the Semimajor Axis, but really it's the distance of the orbit. We can consider it the distance of the orbit. And Mr. Greekin, if it's the distance of the orbit, what unit is used? An AU, an astronomical units used. So very simply put, if I said the period of the planet was 2 years, what's the distance of the orbit? P's 2. What's 2 squared? 4. How do I get rid of the cube? got to take the what? Not the square root, but the cube root. So make sure on your calculators you know how to do a cube root. You got to have one or the other. So the cube root, what's the cube root of 4? Somebody go ahead and calculate it. Or Google it. Some of you guys got your, what's the cube root of 4? What is it? The cube root of 4? 4 cubed is 64. What'd you get? 1.5? Yeah, okay. Which kind of makes sense. If we're going to say the Earth is 1, yeah, it makes sense on there. So again, pretty straightforward. All right, I'm going to, questions? 1.6?
If you round it.
All right, whatever you guys calculated it. I want to go over this sheet on what's happening with these graphing these ellipses. So hopefully you picked those up yesterday. Let's look at a coordinate grid. Coordinate grid has how many quadrants?
4.
4 quadrants. All the values in quadrant 1 are what? Positive. X is positive. Y is positive. So positive, positive. How about the values in 2? Negative, positive. How about the values in 3? Negative, negative. And 4? Positive, negative. When you're graphing an ellipse, when you look at, if you look on that paper you guys started working on.
I learned this in like 3rd grade.
Cool. You guys done? Thanks. What they did is do a shorthand for you. Instead of writing out 4 different coordinate pairs, they're doing a shorthand. So they're saying like negative, positive 2.1, that's X. And then Y plus or minus 1.0. This is really shorthand for 4 coordinate pairs. Now, I don't care where you start, but be consistent. People on the assessment, where they screw up on this, they're kind of bouncing around. And what I mean by being consistent, I like to do the 2 positive x's first. So 2.1, 2.1, and then the negative, negative 2.1, negative 2.1. Then I'll go through and do positive, negative y's. 1.0, negative 1.0, 1.0, negative 1.0. There's my 4 coordinate pairs. I don't care if you want to start with negative x's first. It doesn't matter. But be consistent. Then from there, you can just plot the data points. And notice you'll have 1 data point in each of the 4 quadrants. When you do that activity, some of you I know started, you can either do 6 separate coordinate graphs, or you can put them on 1 coordinate graph, but use colored pencils to show the difference. Either way is going to work. People have done that. Also, we're going to start with Kepler's third law. So this sheet's up there also. And it's fairly straightforward. Oh, you picked it up on the way in. All right, that's about all I've got to add. So you guys can go ahead and get rolling.